Hi, this is Dr. Imanacker. In this video, we're going to continue looking at various optimization problems that are commonly encountered. This one's going to be looking at can design. You may think cans aren't very exciting and really who cares about cans, but go look in the stores, whatever grocery store you shop in or whatever department stores you happen to be in or wherever. You'll see oftentimes cans are one of the most common forms of container to package and move various products. What we're going to look at in this particular problem is how do you go about designing a can that will reduce the amount of material required for the can. We're going to continue keeping in mind the general steps to solving an applied optimization problem. Those steps are outlined here. The first thing to do is to carefully read through the problem and develop a mathematical model of the situation. While this is just a quick sentence to blurb through, this can take a great deal of time. Reading through a problem and understanding what the problem is saying is often accomplished by not reading the whole paragraph or the entire description at once, but by reading a sentence at most, or even just part of a sentence, and pulling that apart to understand what that part is referencing. Developing a mathematical model of the situation proves challenging in that oftentimes we have kind of a natural feel for what's going on, but turning that into an equation isn't something you've had a great deal of experience with in the past. So what we're doing here is developing your skills on taking situations that you're accustomed to and converting them to a mathematical model that can be carefully analyzed, and from that, a decision made. Okay, once we get the model, the steps from there on out are pretty straightforward. You take the derivative as usual. Remember, the derivative is the slope. And we want to always be locating max or min points. Max and min points occur, as I'm drawn in the upper right corner, in locations where the tangent lines have a slope of 0. So we're always going to compute the derivative, set this derivative equal to 0, and solve for the values that come out. Once you get values for x or whatever the variable is, you then want to be careful. Not all the values may make sense in a real world situation. For example, if you're trying to determine how many inches long something needs to be, one of the values might be 17 inches and the other might be a -4. While a -4 makes sense in a mathematical setting, measuring something out in -4 inches, that's not going to work in the real world. So be aware of the values that you're presented when you solve. Remove any values that in a normal physical setting don't make sense. The next thing you want to do is with these values that seem to be eligible for a solution, you then want to verify that each of those is a max or a min. You absolutely do not want to be minimizing cost only to discover that you've chosen the value that creates the largest possible cost of all answers. So you're going to use the first or the second derivative test to confirm the values are a max or a minimum point. Once you've identified your max points and your min points, you're then going to want to go through and choose the absolute max or min that fits within the confines of the situation. For example, suppose you have 50 pounds of a particular alloy available today for production. If one of the solutions requires 80 pounds of that alloy, that's obviously not a solution that's going to work. So what you're going to wind up needing to do is to make sure that when you come up with answers, they are answers that will fit within the confines of the situation. The last thing you want to do then is to write in sentence form an answer that identifies the specific question. For example, in the problem below here, it's going to ask us what dimensions will minimize the material required. So you're going to want to create a statement that says these are the dimensions of the can. And then if you think beyond that, when you're talking with your employer or with a client or whomever, oftentimes they'll have other questions in addition to just how many inches is it. So what you're going to want to then do is consider what are the other likely questions and come up with answers to those as well. That way you're well prepared when you go into the meeting. Let's take a look at this problem below. We're told that a cylindrical can needs to be designed to hold 15 cubic inches of product. What dimensions of can will minimize the total material required for the can with a top and a bottom? Several years ago, I was at a presentation by an engineer who works for Campbell's Soup Company, and he explained that developing a can that uses the absolute minimum amount of material is essential to their company's staying competitive. He said that they produce close to 7 billion cans of soup a year. And even if you're only wasting 1 square inch of material times 7 billion cans, that's a huge amount of steel. That additional steel then adds extra cost to your product. So to stay competitive and to waste no material and come up with a can that will satisfy the needs with the absolute minimum material, calculus is required. Let's take a look at this problem. We have a cylindrical can. There's a picture to the right. You're all familiar with what a cylindrical can looks like. And we need it to have a volume of 15 cubic inches. So I'm going to put down the volume needs to be 15 cubic inches. It's important to keep track of your units. What dimensions will minimize the total material required for the can? So we have this criteria that we have to meet. The volume must be 15. But what we want to do is we want to minimize the material. Okay, so we need to think through where is material used in producing a can? Well, you do need some material for the top of the can. You need some material for the bottom of the can. And remember, the top and the bottom need to be the same size. Okay, then we need material for the side of the can. If you have a top, a bottom, and a side, you have a can. So what we want to do is we want to minimize the material. Well, let's think about how you would determine the amount of material required for each of these pieces. The top is a circle. Now, if we're talking about material, we're actually talking about area. So over on this picture of this lid, we're actually asking what is the area of the lid? Well, the area is going to be pi r squared. The same thing is true for the bottom. It's going to be pi r squared. Now, the side of the can, okay, the thing that actually creates the structure, is actually made from a flat sheet of steel. You can see in this picture, this is actually the label off of the can. When you take this label and you take one of the corners and you fold it over to the other corner, you now have not a rectangular piece of material, but you now have a can. Well, okay, so for the side of the can, I will go along with the idea here that it's a rectangular piece of material. So that's going to be length times height for the area. Okay, so how do we figure some of this out? The length is the measurement that's straightforward for us to get. The length is that measurement that is demonstrated with the orange arrow. Remember that when we take and fold this label around, looking up at the top of the can, that length is now the circumference of the can. Okay, so the side is going to be the length times the height, and the length is the circumference. Well, to get the formula for the circumference of a can, all you do is you take the derivative of the area formula. You take the derivative of pi r squared, which gives us then that the circumference is 2 pi r. And the height's going to be the height. So the side of the can is going to be described by the formula 2 pi r h. We have these three pieces going together to produce the can. The total material is going to be the top, which is pi r squared, amount of material, plus the bottom, which is pi r squared, amount of material, plus the side, which is 2 pi r h, amount of material. This will simplify some. We can add the pi r squareds together and you get 2 pi r squared plus 2 pi r h. Okay, so we have a formula here. We have a model that will talk about the total material required to construct a can. There is a problem with this formula. The problem is we have two variables. One of the variables is r and one of the variables is h. There are two things here that can change the radius of the can and the height of the can. Well, that may not seem like a big deal, but none of the calculus that we've studied this semester allows us to work with two variables. It's always just been one variable. We will work with two variables, but that's in Applied Calc 2 or in a more advanced class. Okay, so what we need to do is we need to find some way here to work this around so that we can get this down to just one variable. To get it down to one variable, I'm going to use my information about volume. Okay, the volume of a can is the area of the base, or the top, times the height. Imagine if you were to stack a bunch of potato chips like Pringles, one on top of another on top of another. The stacking of them fills the void or the space in there. That's the volume. We know in this case we want to have 15 cubic inches, and the volume is going to be the area of the base times the height. Well, the area of the base is pi r squared, a circle. The height is h. From this, we can solve for h. H is going to wind up being 15 divided by pi r squared. Now this is kind of handy because what it allows us to do is to come back to our equation for the total material required, and I'm going to take this 15 over pi r squared and substitute this in for h. So what this allows us to do then is to say, okay, the material that we need is going to be based on one variable, the radius, and you'll see that in a minute in case you don't see it now. It's going to be this 2 pi r squared plus the second term is 2 pi r times h. Well, the h is 15 over pi r squared. This will simplify. We have our 2 pi r squared for the first term. Now, in the second term, remember that this 2 pi r is really a fraction itself. It's over 1. So we can start multiplying here, and we're going to have the 2 times the 15 is going to give us 30. We will have some things that cancel. For example, the pi in the numerator and the pi in the denominator cancel. The r cancels with one of the r's down in the denominator, and this leaves us with over r. So this second term simplifies to be 30 over r. Notice the only variable now is r, so I can list m of r being the only variable. Okay, this is probably the trickiest part of the whole problem, coming up with an equation that describes the material needed to build the can. From that point, it's a series of steps that should be fairly common, or not common, but familiar to you at this point. We're going to take the derivative, set it equal to 0, solve for r. So the next thing we're going to do here to make this a little bit easier is I'm going to rewrite this as 2 pi r squared plus 30 times r to the negative 1. R to the negative 1 is easier to compute the derivative of. The material based on the radius has a derivative equal to 4 pi r. Now be careful because on the second term, that negative 1 is going to come out front. We have a negative 30 r to the negative 2, which is going to give us 4 pi r minus 30 over r squared. I've rewritten this in this second form because it's easier to then go ahead and set this equal to 0 and solve using the algebra. Solving with a negative exponent gets a little tricky. Okay, so I'm going to focus on this part. And what I'm going to have is a 4 pi r equals 30 over r squared. I'm going to multiply both sides by the r squared, and this is going to give me r cubed times the 4 pi equals 30. Next thing, I'm going to divide by the 4 pi, which is going to give us r cubed equals 30 over 4 times pi. To compute r, I'm going to take the cube root of this 30 divided by the 4 pi. When you work this out on your calculator, what I'm basically going to do here to do the cube root is I'm going to do parentheses 30 divided by parentheses 4 times pi, close that parentheses, close another parentheses. Cube root means raise it to the 1/3 power. So I'm going to raise this to the 1/3 power. And the way I've actually entered this into the calculator reads like this. 30 divided by parentheses 4 times pi raised to the 1/3 power. And when you do that, you wind up with an R value of 1.337, rounding it off to 3 digits. Now, we need to recall what units this is in. Is this in centimeters or millimeters or what is it? Well, if you come back up to the problem statement, way up here, notice our volume is in cubic inches. So this radius is in terms of inches. Okay, before I go any further, what I want to do is I want to verify that this is a minimum. Because if this is a maximum, we've set up our equation wrong, and we definitely don't want to be maximizing the amount of material that we're using in each can. Campbell's Soup would not be happy with that when they're making 7 billion mistakes a year based off of the number. Okay, so what we're going to do is we're going to take the first derivative, and the first derivative is up on that top line. It's going to be the 4 pi r minus 30 over the r squared. And I'm going to take a look at the values of the slope or the first derivative. So these are going to be involved with a first derivative test around 1.337. So I will take and I will evaluate my first derivative at 1 and evaluate my first derivative at 2 to see if it is increasing or decreasing. Okay, so what I'm going to do here is I have my 4 pi r, and I'm going to plug in 1. So I'm going to have 4 times pi times 1 minus 30 divided by 1 squared. Well, that's going to be a negative number, less than 0. Then if I substitute in 2, I'm going to have 4 pi, 4 times pi times 2 minus 30 divided by the radius, or the value I'm using now is 2, square it, you get 4, and this winds up being greater than 0. Okay, so with these two values, I can see that to the left of this critical value, the function has a negative slope, it's decreasing. To the right of this value, the function has a slope that's positive, it's increasing. If you go from decreasing to increasing, what you have at that critical value is a minimum. Okay, so I have verified that we have a minimum. That's very important to do before you go any further. Okay, now we know we have a minimum. We know that the radius is going to be 1.3 or 1.4. That's a little bit under a 3-inch diameter can. A 3-inch diameter can is about the size of a soup can. Okay, so this isn't unreasonably small or big. It's a can that you're used to seeing all the time. Okay, so what I need to do now is I need to compute my dimensions. Because recall in this problem we were asked to determine what dimensions do you need for the can. We need a radius of 1.337 inches. Now, as you talk to people, a lot of people are not real comfortable with discerning between radius and diameter. So you might want to throw in that, hey, the diameter is going to be 2.674 inches, or a little bit over 2.5 inches. The height of the can, well, let's see, the height we found earlier. Here it is at the top of the screen, circled in yellow. It's 15 divided by pi r squared. So this is going to be 15 divided by pi times this 1.337 squared. I'm going to go back up and check my height once more just to be sure. Yep. Okay, so at this point, the height then is going to be 15 divided by pi, and I'm going to do a parentheses here. 15 divided by parentheses pi times 1.337, like that. So what I actually entered in this case is 15 divided by, and the calculator does have a key for pi. It's directly underneath the clear key. And I'm going to do times 1.337 squared. When I do that, I get a value of 2.671 inches. Now that I have this value of 2.671 inches, I have the diameter, the radius, and the height. Those are three values that the client or our supervisor are going to be interested in. They may also be interested in, well, what's the total amount of material required? Well, the total material is going to be equal to 2 pi r squared. I'll come back up here, way up here. Here we go. The total material is now right at the top of the screen, 2 pi r squared plus 2 pi r h. So I have plus 2 pi r h. Then all we need to do is to substitute in the values that we've already computed. This is going to be 2 pi times 1.337 squared plus 2 pi times 1.337 times 2.671. And remember, this is going to be amount of steel that's used. So that's going to affect what we're going to report our units in. So I've got the 2 times pi times 1.337 squared plus 2 times pi times 1.337 times 2.671 equals. This gives us then 33.6696. Now, when we round this off to three places, it's going to be 33 point. This says to round this up. Well, that's going to come up one. and it's going to be 0.670. We do not want cubic inches. Cubic inches talks about volume. What we're now talking about is the surface area, and the surface area is inches squared. Okay, so let's go back through this and figure out what all we have said. What we have said here is we can achieve this volume of 15 cubic inches by using a can that has a radius of 1.337 inches and a height of 2.67 inches. The total material used will be 33.671 inches squared. That may seem like a whole lot to try and put down, but let's go ahead and see about typing that out. Okay, so when I type this out, we can state it as follows. The can needs to have a radius of, what was that? 1.337 inches. I may want to put in here diameter of 2.674 inches, just as a side note, and a height of 2.671 inches. The total material required will be 33.670 square inches. If you come back to your employer or supervisor, whomever it is, with an answer like this will make some sense. They know the radius, they know the diameter, they know the height, and they know the total amount of material used.